Okay, in this last video, we're going to talk about the first and second laws of thermodynamics. Some of this material is going to come out of chapter 15. Some of this material comes out of chapter 16. But we are not going to have time to do a thorough coverage of chapters 15 and 16. So we're going to start in chapter 15. And in particular, section 5. Okay. First of all, I want to say, what are we talking about when we talk about thermodynamics? We probably use the word in chapter 14, but we may not have defined it. Thermodynamics is the study of energy relationships. That involve heat, mechanical work, and more. We're not going to study the more. We're going to talk very much about the thermodynamic relationships that involve heat. You'll remember heat is an energy flow that's caused by a temperature difference between two systems or two objects. And of course, mechanical work we've studied before. Mechanical work is when you apply a force through a distance. There's basically two ways that we think of a thermodynamic system interacting with its environment. So, let's assume this is a thermodynamic system. Two types of systems that come up a lot in thermodynamics are refrigerators, which are designed to remove heat from the system and dump it out into the environment, or heat engines. Heat engines are designed to take heat from the environment, you put heat into them, and they do work. Think of something like an old-fashioned steam engine. Okay, you put fuel of some sort in, some type of heat. It's what you do when you put gasoline into your car. You put in a fuel, and you have combustion. You have an internal combustion engine, and that heat, that energy stored inside that, does mechanical work. So in this first example, let's say if we add heat, into the system is considered to be positive heat. So this would be positive heat. We put heat into this system and we get work out of the system. So work done by the system is positive work. Different textbooks can use different sign conventions, so you do want to pay attention. But our textbook, and the one that most of the books I've used, consider any heat added to the system as being positive heat. Any work done by the system is positive work. There's another, this would be typical of a heat engine. That's one scenario that we see a lot. The other scenario that we see a lot looks slightly different. It would look like a refrigerator. In a refrigerator, we do work on the system. I don't know how familiar, but refrigerators have motors in them and that expand and contract gases and things, but they do work on the system. And the result of doing work on this system is that heat is removed. So heat removed from system is negative. So in this particular example, Q would be less than 0. It would be a negative quantity. And in this case, work done on the system, we do work on the system, that is considered negative work. So again, in this case, the quantity of work would also be less than 0. So heat added is positive, heat removed is negative. Work done by the system is positive. Work that's done on the system is negative. You just have to get those signs correct. Now, there are a lot of different thermodynamic processes. You can have thermodynamic processes where everything happens at a constant temperature. You can have thermodynamic processes where things happen at constant volumes. We're going to look at a thermodynamic process where we have a constant pressure. This is really probably the very simplest one for you to understand. It's certainly, there are at least 4 others that I can think of. So, but we can't study all of them. So we're going to look at an isobaric. Anytime you see iso, you know nothing's changing. An isobaric process, which is a fancy word that means constant pressure. Now, we didn't do all the work about ideal gases, but you've all had high school chemistry. So you all know that in an ideal gas, you have that relationship between pressure, volume, and temperature. In fact, the ideal gas law, PV equals nRT. Okay. So when I say we have constant pressure in our gas, it's entirely possible that the volume is changing and that the temperature is changing. And if the volume changes, the temperature will probably have to change if we're going to maintain a constant pressure. Okay, but that's the only thing that we are considering. So we're going to start with this idea of a cylinder of gas. And it has a moving piston. So that would look like this. Here's our cylinder. It has like a handle, you can kind of think. And at maybe one point we were at some smaller volume, but we expanded the gas and we moved the piston out to here. So we had a change here. We're going to call that delta X. And all of the gases that we're talking about, we're going to treat them as ideal gases. So in this case, you can see, although we're going to maintain constant pressure, we're definitely going to change the volume because we're going to start with this smaller volume, we're going to go to this larger volume. Now, we have to define a few more things. Pressure in physics is simply a force per unit area. So, if you have 500 newtons of force over a 1 meter square area, you have 500 pascals of pressure in the SI system. So it's the force in newtons divided by the area in square meters. That'll give you the pressure in pascals, which of course is the SI unit for pressure. If we think about this and we rearrange this, we can see that pressure equals F over A, or F is equal to the pressure times A. Okay, so I'm going to come back to that in just 1 minute. I can solve pressure equals force over area, force equals pressure times area. Okay, we know that work in physics is the force times the displacement. So the work done by this gas when it expands and pushes this piston out, if a gas is expanding, it actually is doing work on its environment. Think about that. When you blow up a balloon, the gas inside the balloon is pushing against the walls of the balloon. It's doing work on its environment. So the work done would be the force times the displacement, delta x. However, we just said in this case, we can rewrite the force as pressure times area. Well, think about that for a minute. The area in this case is the area of this cylinder. That's what that's pushing against. That's force, that's the area. Well, the area of that cylinder times delta x is actually the change in volume. So what we see is for an isobaric process, the work done is the pressure times the change in volume. If this change in volume is positive, in other words, the volume increases, then the gas did positive work. The gas pushed against it and expanded its environment. If we go the other way and we push against this piston and we compress the gas, that means the volume gets smaller and we would be doing work on the gas. Work would come out to be negative. But this is a really easy formula for work. It can also be written, as work equals the pressure times V2 minus V1. There's really no difference, just another way of thinking about it. All right, so far we're good. Let's go back for just a minute and think about that system that we have. Let's go back to the heat engine one because it's pretty logical. We put in some work, we put in some heat, and as a result, it did some work. Heat in, work out. The first law of thermodynamics states the following. The change in the internal energy of a system internal energy is sometimes also called thermal energy. It's the energy that every object has simply because all of the particles that make up that object are in motion. Every molecule in the universe is in a state of constant motion. So all of the molecules that make up this marker are vibrating. This marker has a certain amount of internal energy. If I were to heat it up, I would be adding to its thermal energy or its internal energy, because if I heat it, I know its temperature goes up. That means all of the molecules are vibrating faster. Remember, temperature just tells you something about the average kinetic energy of all of the molecules. When you add heat, those molecules move faster. That temperature goes up. So, the change in the internal energy, that thermal energy of a system, is equal to the heat added. So if I add 10 joules of heat to my system, the internal energy went up by 10 joules. That's conservation of energy. That's all that is. So a system is equal to the heat added to the system minus any work done by the system. Symbolically, we usually write the first law like this. The change in internal energy, remember U is our symbol for any type of potential energy or stored energy. The change in internal energy is equal to Q minus W. If you put in more heat than the amount of work you do, your internal energy is going to go up. People are a perfect analogy. If I eat 2,000 calories, I'm adding heat to this system. If I only burn 1,500 calories, I only do 1,500 calories worth of work in a day, then my internal energy just went up by 500 calories. I took in 2,000 calories, I expended 1,500 calories, it went up as 500 calories. I'm going to store that as fat. That's what people do. But that's what the change in stored energy. Fat is stored energy of your person. So, perfect sense. It's conservation of energy. If you do more work than the amount of heat that you add, let's turn that problem around. You only eat 1,500 calories, but you burn 2,000 calories. Your heat in was 1,500. The work you performed was 2,000. Well, then your internal energy has to go down by 500 calories. Your stored energy has to decrease. You're going to burn some of those calories stored in that fat and lose weight. It's just basic conservation of energy. It's a restatement of conservation of energy. We can't create energy and we can't destroy it. It has to go someplace. If we add 500 joules, then the system's energy has to go up by 500 joules unless we do some work. If we add 500 joules and we do 400 joules of work, then it's only going to go up by 200 joules. It's a really easy concept. Change in internal energy is the heat added minus any work done by the system. So let's work an example. So this example has to do with boiling water at a constant pressure of 1 atmosphere or 1.013 times 10 to the 5th Pascal. So that's 1 atmosphere. If you boil 1 gram of water, it expands from 1 cubic centimeter to 1,671 cubic centimeters of steam. The heat of vaporization is 2.256 times 10 to the 6 joules per kilogram, or a little easier since we have this in 1 gram of water, it's 2256 joules per gram. First question, how much work was done by the water? How much work is done by the system? Well, the work is the pressure times the change in volume. The pressure has to be in pascals. And the change in volume has to be in cubic meters. We have it in cubic centimeters. 1671 minus 1 cubic centimeter is a change of 1,670 cubic centimeters. But I know that 1 meter is 100 centimeters. But I have to cube that. I have to do that 3 times. So my conversion factor is 1 cubic meter is 100 cubed, which is going to be 1 million cubic centimeters. So I'll have to make that conversion. And when I do, I will come out that the amount of work done was 169 joules. So the work done by the gas is 169 joules. So not too difficult. How much heat did we have to add to the system? Let's get the heat added. To get the heat added, let's do that real quick right here. The heat added is the mass times the heat of vaporization. If we use this second one, we have 1 gram times 2,256 joules per gram. So with the heat that was added was 2,256 joules of heat. There's only one thing left to do, and that's calculate what was our change in the internal energy. It is equal to the heat we added minus the work that was done, and that came out to be 2,087 joules. Now, I've been pretty loose with significant digits. I think the entire problem probably had at least 3 significant digits, but I didn't write all of that down. Parts of it I know had 4. I had 4 for this and 4 for that. I might have even had 4. If I had 4, then this would definitely be my final answer. I'm going to leave it like that. Like I say, I don't have the original in front of me. Okay, so that gives us a basic understanding how to find work done by gas for constant pressure. We already know how to calculate how much heat we have to add, in this case, to turn a gram of water to a gram of steam. It did tell us that we were at 100 degrees Celsius, so we didn't have to worry about heating up the water or anything. Okay, let's think about this. Does it make sense? Would we expect a gram of steam to have more energy than a gram of water? Absolutely, we would expect a gram of steam to have more. We know that in gas form, the molecules are moving much faster than they are at liquid form. It's that extra thermal energy that's sort of how it escaped, right? Okay, so now we're ready to move to chapter 16. And in chapter 16, we're really just going to look at section 7. Now we want to talk about two ideas. One is entropy, and one is the second law of thermodynamics. First of all, we need to know what entropy is. Entropy is a quantitative measure of the disorder of a system. Now, we are not going to worry about how do I calculate entropy. We just need to know that we can calculate it, and it can have a number assigned to it. But generally, we're pretty good at figuring out which system is more disordered than the other. If we think about phase changes, for water, ice is the most well-ordered form. It has the least amount of entropy, disorder. Then water definitely has more disorder, more entropy, as those molecules are free to slide around. And then finally, if we change it into gas, that will have the most entropy, the most disorder. Okay. Natural processes, and when I say a natural process, I mean things that occur in nature. If you just leave things alone, what will happen? Natural processes always have a preferred direction. Think about it. If I have something cold and I put it in contact with something hot, the heat will always flow this way until it reaches equilibrium. That's because of entropy. That's because by doing that, it creates the most disorder. Nature likes the disorder. That's what, now you say, well, Ms. Hughes, of course that happens. But this does not violate, if I said that the heat went this way, that would not violate the first law of thermodynamics. The first law of thermodynamics just basically says you have to have conservation of energy. I should be able to take 10 joules of heat out of the cold, put it into the hot. The cold gets colder, the hot gets hotter. And I can do that. There are ways to do that if we use work. But that won't ever happen naturally. In a natural process, there's a preferred direction. And the preferred direction for heat flow is always from a hot object to a cold object. There are other transformations of energy that also have preferred directions. It's very easy to convert mechanical work into heat. You step on the brakes on your car, you convert that mechanical energy to heat. You generate friction, the car stops. It's really much harder to convert heat to mechanical energy. We do it, we can do it. We do it in our car motors all of the time. But just in general, once you've taken that mechanical energy and friction's operated on it, it's hard to recover it. Does that make sense? Think about swinging a pendulum. If you start the pendulum moving, it will gradually die down because of friction. That energy was lost to thermal heat, which just went out into the larger environment. It's really, really hard to recapture that. So again, we kind of have this preferred direction. And the preferred direction is always the direction that increases the entropy of the universe. So let's think about those systems that we talked about earlier. And in particular, ideally, all of the heat added to a heat engine would be converted to work. So ideally, if this is a heat engine, this is what I want to happen. I want the heat in to equal the work out. If I put in 1,000 joules of energy, I want to get out 1,000 joules of work. Reality, that doesn't happen. It can't happen. It will never happen. What will happen is you'll get work and you'll get waste heat. And this cannot be eliminated. There's been mathematical proofs to show you cannot actually eliminate it all. But think about it. Think of all the heat that your car engine generates. They get really hot in there. That's why you have to have fans and radiators and coolants and all of that thing. That heat doesn't cause the car to roll forward. It's a waste product. It's a byproduct. So your thermal combustion engines that run your cars, they're pretty inefficient. And I think I'm going to be wrong if I say a statistical number, so I won't be exact at all, but I think it's close to half. Only about half of the energy stored in that gasoline actually propels your car forward. The other half, give or take, and I don't know whether it's 30% or 40%, is wasted. Now, obviously there are more efficient engines. In fact, the most efficient engine is something called a Carnot cycle engine. But regardless, even a Carnot cycle engine is going to have waste heat. Okay, so we can write the second law of thermodynamics is written in a lot of ways. One of the ways, I'm not going to write this because you've got it in your notes, if you print off my notes, is called the engine statement of the second law. And the engine statement for the second law says it's impossible for a heat engine to convert 100% of the heat to work. It's impossible. Okay. That's a statement of the second law of thermodynamics. What the first law of thermodynamics basically said is you have to have conservation of energy. So you can't get more work out of something than the amount of energy you put in it. Conservation of energy. If I put 1,000 joules in, I can get 1,000 joules out. I can get more out if I use some of the internal energy. You could have stored energy. But the first law says I have to have conservation of energy. The second law says I can't ever have 100% efficiency. I can't break even. If I want to accomplish 900 joules of work, it's probably going to take me at least 1,000 joules of energy put in. Okay? This waste heat increases the disorder of the environment, and that just happens. Okay. Secondly, ideally all of the heat removed from a refrigerator would equal the work done on the refrigerator. Okay, refrigerators are sort of the reverse process, but ideally with a refrigerator, you do a certain amount of work on the refrigerator, and as a prize, it removes that much heat from the refrigerator. That's our goal. That's how we keep our food cold. But what happens, in fact, is, here's our refrigerator. You do a certain amount of work, but even when you're doing the work, you generate waste heat. The motor in the back of the refrigerator is generating heat even while it's doing work on the refrigerator. So let's make up some numbers. You might do 1,000 joules of work on the refrigerator, but what you find is you're dumping 100 joules out into the environment just by the heat you generate doing the work. And that means you can only remove maybe another 900 joules. But you won't break even. You're going to have to do more work than the amount of heat that you get. And what you find is the amount of heat gained by the environment then is more than the amount of heat removed by the refrigerator. Think about it with numbers. We do 1,000 joules of work. That generates 100 joules of waste heat. And it takes out 900 joules from this. So yeah, the refrigerator is cooler. It lost 900 joules of heat. But the kitchen got hotter by 1,000 joules of heat. Okay. There is a statement for the second law of thermodynamics. It's written in the refrigerator form. And the refrigerator form says, it's impossible for any process to have the sole result of transferring all heat from a cooler to a warmer environment. There's no process that you can do that will make all of the heat go from a cooler to a warmer environment. Some of that heat's just going to stay in that exterior environment. Those are both good statements. They're not my favorite. I prefer the entropy statement. And the entropy statement is basically based on this system, this statement. In every natural process, entropy increases if all systems in the process are included. Okay, there's a couple of really important words. One is we're talking about natural processes, things that occur in nature. And we have to look at all systems, not just some systems, because if we're not careful, it may look like that natural process is creating order. And there's some really excellent examples. Let's suppose you have a seed and you plant a seed and this very structured plant grows. You get a beautiful periwinkle. That periwinkle's really well organized. And you say, well, that's natural and that really looks like it's creating order, Miss Hughes. It does look like it's creating order. But you have to remember that that periwinkle is taking energy from the sun, it's doing photosynthesis, it's releasing carbon dioxide gases, it's taking nutrients from the soil. When you look at every part of the system, the sun, the rain, the dirt, the humidity, the total entropy of the universe actually increases. Just like a child growing. A child's a very well organized natural thing. But it won't continue that unless you continue to add lots and lots of energy. Or feed them lots, right? And in that process of adding all of that energy to allow that growth, they take all of that energy that was stored in that food and they, create disorder. You don't have milk anymore. You don't have meat anymore. When you look, they have byproducts, lots of diaper changes with little ones. They're creating as much disorder to the universe as the order that's being created in them. Think if you've ever had an infant or a small child in your house, you can kind of start to realize how much work and energy has to go into that little tiny system to make such a well-organized thing, and how much disorder it also creates. So, the second law of thermodynamics, if we write it in the entropy statement, says this. In all processes, the total entropy remains the same or increases if all systems in the process are included. Now, in order to have a process where the total entropy remains the same, that's not going to be a natural process. That's probably going to be something very carefully controlled where everything remains in thermodynamic equilibrium and evolves very slowly. But in natural processes, that entropy always goes up. So a result of this is the entropy of the universe is always increasing, always. Now, you guys heard at different times people talk about, back in the 70s, before you were all born, there was a big energy crisis and gas prices were high and people were waiting in really long lines to buy gas, and I'm sure it all had to do with foreign trade relationships with the oil-rich countries. But regardless, you say, if we can't create or destroy energy, how in the world can we have an energy crisis? How in the world can we run out of energy? And the problem isn't that we can run out of energy. It's that we can run out of usable energy, energy that's easily accessed. The energy that's stored in fossil fuels like oil and coal, it's very well ordered structurally. It has really low entropy. But once we burn that coal or that oil, we have taken energy that was in a really low entropy, high structured form, and we've converted most of it to just waste heat that's not ever easily recovered. We didn't destroy the energy, but now it's got really high entropy and it's really not user-friendly energy anymore. So that's really the problem. Okay, so let's go back through the three laws of thermodynamics. The zeroth law was just thermal equilibrium. If A has the same temperature as object C, and B has the same temperature as object C, then A and B must have the same temperature. Nothing to it. The first law is conservation of energy. The internal energy of a system, whatever that system is, will change by some amount equal to the amount of energy you put in, usually heat, minus the amount of energy you get out, usually work. It's just conservation of energy. You can't create it or destroy it. The second law is not conservation of energy. Conservation of energy still is in play, but it simply says that in all natural processes, the entropy will increase if you think about every system involved in the process. Now, the entropy of some things may go down and the entropy of other things may go up. If we think about the hot block and the cold block, and the heat transfers like this, what's going on? Well, the entropy in this block actually does go down. As it cools, it's more ordered, its entropy goes down. But the entropy of this block goes up, and it actually goes up by an amount greater than what this goes down. So by the time this reaches thermal equilibrium, we've had an increase in the entropy of the universe. If you have a cup of hot coffee and you pour a little cold milk in it, when you pour that cold milk into that hot coffee, the entropy in the coffee actually does go down slightly as the coffee cools. The entropy of the milk goes up dramatically, and it disperses all throughout. Think about a glass of water, and you get a drop of food coloring. If you very carefully place a drop of food coloring on top, that's going to be its most well-ordered moment. All of the food coloring will be in one spot, but then naturally, without us doing anything, those random vibrations of particles and that food coloring will disperse through the whole glass of water. You come back a little while later, and you got pink water if you use red food coloring. And there's nothing you can do to get all of that food coloring back into a drop. That disorder is permanent. You can say the same thing for perfumes and smells. If some child breaks out a bottle of perfume over in one corner of a classroom, it doesn't take very long before the entire classroom smells that perfume. That perfume was really well ordered while it was inside the container. Let's assume a little glass vial. But as soon as she let a little bit of it out, it dispersed all over the room. Okay? So there's our 3 laws. They're not hard to understand. And that's the end of Physics 1401.